Assalamu alaikum. I'm Rafis Chaudhary. Today, I'm going to present our work and optimizing sensor placement for air quality monitoring using hybrid simulated annealing genetic algorithm. Here, my teammate is Azharul Karim Chaudhary Onik. At first, we're going to talk about the problem definition and motivation. Air pollution is a major environmental concern, with PM 2.5 being a significant contributor to respiratory and cardiovascular diseases. Deploying air quality sensors is crucial, but high cost necessitates optimal placement to ensure maximum coverage with minimal redundancy. Traditional approaches such as rule-based greedy algorithms do not guarantee the best placement. Meta-heuristic approaches like simulated annealing and genetic algorithms provide robust solutions for such complex optimization problem. Our objective is to maximize PM 2.5 coverage while minimizing the number of sensors required. And now we're going to talk about the literature review. Several methods have been explored for sensor placement optimizations. Greedy algorithms such as those proposed by Smith et al. On 2020 offer quick solutions but may not be optimal. Genetic algorithms by Jones et al. On 2021 improve efficiency but lack refinement. Particle swarm optimization have been used in various studies, but hybrid approaches remains underexplored. Our contribution is the introduction of hybrid simulated annealing genetic algorithm, which effectively balance exploration and exploitation to achieve superior sensor placement results. We have used hybrid simulated annealing genetic algorithms. Our approach integrates the strength of simulated annealing and genetic algorithm for sensor placement optimizations. Here is the workflow of our works. At first, we have initialized randomly. We randomly generate sensor placement. After that, the fitness evaluation comes in. Each placement is evaluated based on PM 2.5 coverage. After that, we have done some selection. The best candidates are chosen using a roulette wheel mechanism. Single point crossover is applied to create new sensor placement. Mutation, random changes are introduced to maintain diversity. And the simulated annealing helps refine solutions by escaping local optima. And the termination, the process stops after a predefined number of generation or when improvements are triggered. This hybrid approach leverages the global search capability of genetic algorithm and the local refinement ability of simulated annealing to improve optimized results. Our experiments utilize the PRSA dataset, which contains hourly PM 2.5 measurements for 12 monitoring stations in Beijing. The study area was divided into 30 grid with 20 sensors placed. Each sensor had a coverage radius of 2 grid cells. The algorithm ran for 50 generations with a population size of 50. Results showed that our hybrid simulated annealing genetic algorithm approach achieved 90.59% coverage, outperforming the other methods while ensuring optimal sensor placement. The computational time required was 300 seconds, which, while higher than simpler method, delivered significantly improved accuracy. The table below summarizes the performance of our approach compared to existing methods. Here, random placement have coverage of 50 to 70% and runtime is 10 seconds. Greedy algorithms have coverage of 80 to 50% and the runtime was 120 seconds. And here is our hybrid simulated annealing and genetic algorithm approach, which have a coverage of 90.59% and the runtime was 300 seconds. Our method significantly outperforms random and greedy algorithms in terms of coverage, making it valuable solutions for real-world air quality monitoring applications. To better illustrate our findings, we have developed an interactive map showing sensor placement and their coverage. If you click on the link, we'll go to the interactive map. Here, the green marks indicates the sensor locations and the blue circle represent the coverage area. And this visualizations allows for dynamic exploration of optimized sensor placements and highlights how our approach effectively prioritizes the high PM 2.5 regions. You can explore this interactive version of the map using the link given in the presentation slide. While our approach delivers high coverage, some limitations remains. Fixed sensor radius, real-time conditions may vary. Computational cost is higher than greedy approach and have some scalability issue. Performance may degrade with large grid. Feature work will also be explored. Dynamic sensors are ADII to better reflect real-world conditions. Multi-objective optimization to balance the cost and accuracy. We can also use parallelization techniques to improve computational efficiency. In summary, our work presents a hybrid simulated annealing and genetic algorithm approach to optimize air quality sensor placement. Our method achieved 90.59% coverage, significantly improving upon traditional methods. This works pave the way for smarter, more efficient air quality monitoring system. Future research will focus on enhancing efficiency and adaptability for real-world conditions. Thank you for your time and attention. We are happy to answer any questions you may have.